she has some really significant contributions to theoretical physics. And one of the big things that she has contributed to is actually just understanding gravity in one of the simplest possible settings, which is gravity in asymptotically flat spacetimes. And so Sabrina has like major contributions to our understanding of that, both in the classical side of things and also in the quantum side of things. And I think she's going to tell us about some of that today. So
basically the goal for today's talk is kind of fourfold, or at least maybe the first three are goals, and the fourth is just rambling at the end. Basically, I want to introduce the celestial holography program and motivate why we were doing it and like what kind of is the origin story. And I want to spend a lot of time more on like the motivation and then the kind of earlier parts of it with the asymptotic symmetries and the second section, because I think that that's like the thing that is basis dependent. It's like a lesson that we want to keep going forward. So first, why holography? I think that at least at perimeter we have different groups. I think the quantum gravity group is not quantum fields and strings, and quantum fields and strings is basically former string theorists who are doing whatever they're doing, mostly quantum field theory. But I'd say the majority of people at perimeter will accidentally say, if you're asked like, what do you work on or why do you do what you're doing? We're trying to do quantum gravity. And so the motivation again for this is just, I think a lot of like fundamental theorists believe that why we do what we do is because we think that nature is surprisingly simple, and there's some kind of impression that you can get when you find a theory that explains things at like different energy scales. And so this quest of trying to merge like our description of very short distance physics with a consistent description that would also contain very large distance physics, which is general relativity, say, kind of is the underlying theme in a lot of what people do. So not only that is my motivation, we want to understand quantum gravity, and we want to play with it in contexts that are really relevant to real world stuff. So of all the things one could do studying quantum gravity, I'm sure there's many things I'm going to not even allude to. But kind of two routes. So like the one in my, I guess, pedigree with like Andy and whatnot, they saw string theory as a resolution to some of the problems that were in the little premise in the last slide, which is that if you just treat your Einstein-Hilbert action as a normal quantum field theory, you run into some funny issues with like whether it's normalizable, and also the fact that you want to think of GR as saying that your method is responding to whatever matter is going on. It's maybe not natural to always think of things as just a fixed background. So some people posit that at very short distance scales, that basic description changes significantly, and like the particle structure is coming from this world sheet theory, and that's all we need. And if you do that and you push it very far, it turns out from like Juan Malacena and lots of people afterwards that there's some interesting realizations where you have a quantum theory of gravity or strings in ADS and a equivalent description of the boundary which is ADS 15. Now at the same time, you could have maybe ignored some of this and been like Hawking and just say, I want to put my quantum field theory in a curved space-time. When I have a horizon, I'm going to have some evaporating here. And some deep questions about whether or not that process is unitary or why this black hole looks durable, but like I still want my theory to be unitary. There's kind of two hints, I guess, at this notion that gravity could be holographic. So on the one hand, it's this explicit realization, that I have it, of some ADS-CFT correspondence. And on the other hand, it's that this black hole somehow behaves like a thermal system with an entropy that scales like an area law. And so from all those different ways, there's kind of a distilled idea, which is that perhaps like any theory of quantum gravity would have an equivalent lower dimensional description without quantum gravity. And so from the point of view of the motivation, like I was saying at the top, is can we just cheat? So quantum gravity is hard. Can we try and see it for free by finding this dual description without gravity? And now, I guess kind of the beauty and or maybe like a thing to be scared of is, say we just say that we have all of this machinery that really came from understanding like this like 10-dimensional or whatever, like this fundamental description you have in string theory, and in ADS-CFT you're realizing this holographic principle. When you jump and try to say I'm going to let that be the guiding point and that be the general thing, and then build things from the bottom up, you might kind of be less motivated. But it's a kind of an interesting, I guess, notion that in physics we often have kind of ideas that seem to be true for a lot of wide variety of things. Then we posit that that thing is the guiding principle, and then you try to generalize. So that's what we're doing, but now not necessarily for ADS. So challenge that we have is that this example of holography where we think we understand quantum gravity because of an equivalent non-gravity system that's quantum that we understand is string theory, and it's also a space-time with negative cosmological constant. And so you can think of that as gravity is in a box for you. And so that's cool, but that's not what the real world is like. And so we're going to try to generalize that in this term. So to be fair, I'd say like, so Strominger actually kind of, if you look at like before I was a grad student, a lot of his work you could say is along the lines of trying to just generally apply holography to different like physically realistic reviews. And so in particular, if you zoom into like a very highly spinning for a black hole, there will be basically an ADS geometry in there. And so this curse CFT correspondence is trying to use like normal ADS CFT in a more astrophysically relevant setting, where I guess they're using that symmetry to kind of mesh some waveforms for like some radiation coming out of the horizon region. Now, like Alex also does that. That's cool. Okay, and many others. So of course, unless you believe Desi, maybe, we live in a de Sitter universe, and so we have this positive cosmological constant. It's a very small one, so I'm not going to talk at all about de Sitter CFT, but a lot of people do work on that now. And instead, I'm going to say that instead of being a flat earther, I'm a flat universer, and I'm going to pretend that lambda is actually 0 because what is 10 negative on Earth, right? And then the reason for that, so if you want to say it's because it's supposed to be the real world, that's not good enough. But if I want to say that whatever framework I have for describing asymptotically flat or like flat spacetimes should cover a very large range of scales, then that's probably good enough motivation. And so in particular, the things that I'll talk about today, there's analogs of these effects, say for some collisions at CERN. Or you could go out and look at gravitational waveforms that LIGO is going to measure, or future like Lisa space-based detectors would be better for some data. And so it's neat that for a very, very like wide range of scales, we can just ignore the cosmological constant, and we're going to try to build a version of some ingredients of that hologram that we think would try to capture interesting statements about the positive things. So that's the motivation. That's good. And so that's why holography. Now I want to try to convey, I think the coolest thing maybe from a lot of this stuff is that the asymptotic symmetries of these solutions with vanishing cosmological constant are very rich and interesting. So if there's one takeaway besides, okay, people do holography, I'm going to try to teach something about 2, and we'll see what would happen. And then for 3 and 4, it's the flavor of the decade or whatever. Like I think that 2 will stay around. So basically, for the main idea for this part is that there are going to be infinite number of symmetries that I'm going to get for any asymptotically flat spacetime. So again, asymptotically flat spacetime is going to be, I'll define it a little bit better, but flat space, lambda is 0. And these asymptotic symmetries are the things that I want to get across, and they're going to be much larger than, say, point array or the kind of isometries of spacetime that you might be used to. Okay, so now if I were to get in Minkowski space, I think whenever you're doing space special relativity, I don't know if that's an undergrad course here or say Vienna, you're often using or taking advantage of the isometries of this metric. And now that's like the simplest solution to Einstein's equations with cosmological constant 0. But of course, you know, like there's stars, there's planets and whatnot. And even if like, so you can either add matter stress tensor, or you can either ignore, like say, look at black hole solution is going to have anything on the right hand side. But I want to basically look at the phase space of solutions to the Einstein's equations with vanishing cosmological constant. And so that class of solutions is this thing that we're going to call asymptotically flat spacetime. And feel free to bother me with questions at some point. I think it slows me down too, and I like really big challenges. Okay, so we're looking at solutions to Einstein's equations. We've set lambda to 0. And then one thing important, I guess, to keep in mind is that like which solutions are physical. So I think that maybe you don't always think about it too much in the undergrad course. If like I just write down some linear vector solution for a second degree charge, maybe you would encounter like, okay, I have some Green's function and I want to know what boundary conditions I should be imposing on that. So basically, there's kind of a delicate thing where these are going to be highly nonlinear equations. And you want to basically be in a kind of good initial value problem, say, and evolve in it. There's a lot of, I guess, like mathematical people that would do it. And for me, the only thing I'm going to care about is roughly the fall offs as I go towards my conformal boundary and the kind of dependence time. So let me first introduce what this diagram is. So basically, the nice thing, as soon as if I don't have a horizon, all of my solutions will roughly have a similar structure at infinity. And so I'm drawing right now, say, a Penrose diagram for Minkowski space, which I could just change my coordinates and do. But I could also think of like that conformal boundary as being a thing that's going to be there for any other metric involved. So what is this Penrose diagram doing? I'm trying to capture the causal structure, but distort distances. And so, for example, like, I don't know how, I probably wouldn't have seen a metric, maybe everybody would not. But you can imagine that, like, if I only care about the fact that something is orthogonal to another thing, I don't care about how long I'm going, that there's some value to being able to squish my entire space-time into this little napkin-shaped thing and have it so that anything that is at a 45 is light, anything that's to the future of that 45, or like, no, pointing up, is going to be time-like, and anything that has a slope that's less than 45 is going to be space-like. And so the thing that I'm trying to capture here is that this is basically just a change of my coordinate system. I'm mapping all of my space-time to this little diamond, but I've kept the angles the same. And so I can keep track of the fact that this notion of going to infinity in different directions is actually different. So fun thing about our asymptotically flat space-times is that if I say I want to go infinitely far away from this place, there's different ways I can go. So I can go in the space-like direction and I'll land at space-like infinity. If I'm just waiting around forever, I'm going to end up at future time like infinity, and I came from past time like infinity. But if I'm null, then I can get out to a component of this boundary that's going to be a null surface itself, and is also like kind of a different kind of place, which is kind of fun. So massless guys go to null infinity and come from past null infinity, and these different directions of infinity are important. But for most of my talk, I'm going to ignore the time-like guys and space-like guys and just talk about null infinity. So good. And then a couple things about it are going to be useful for, I guess, explaining why flat holography is hard or weird. And so I mentioned that not only is null infinity where my massless excitations are going to go to, it's also a null surface itself. And so that feature of it kind of makes the causal structure on it different. And so pullbacks probably are not a good thing to be mentioning. But if I have basically, say, two cones, and I think of like so I'm thinking of like this is the light cone of this point, then you kind of see that there's only going to one ray that's tangent to it. And so what it ends up being is like that if I have any 2 points, say on null infinity, and they're not directly along the same generator of it, they're going to be space-like separated. And so this is very strange metric because I'm normally used to having some light cone. So normally, say I want to think of this phi as some, say, circle on null infinity, so I've like the sphere at infinity where all of the light rays go. Instead of that time evolution being like a normal time direction where I have something could propagate on the boundary and there'd be a light cone, everything just basically goes vertically. And so if I said, and I kind of alluded to this maybe too quickly before, that the whole point of holography is to try to find some sort of dual description, we're a little bit confused because the fact that this time direction is null. So it almost looks like everything's kind of ultra local and just each direction is talking to the other ones, except for so far as there's an in and outgoing path. So that's one hint that flat holography is going to be weird, or the theory of living on that boundary is going to be weird, and maybe motivating some of the kind of tricks we're doing to look at like soft physics first. So causal structure is weird, flat is cool, but it's like it has some good. And then for more, I guess, some equations to see what's happening, I have my asymptotically flat space times. I now no longer just want to be flat space. So this first part here would be the metric for flat space for a very specific choice of coordinates. So I have this retarded time. So it's like my usual, time direction minus my radius. And then I use like some stereographic coordinates on my sphere. The sphere is basically the sphere over every point except for r equals 0. And then now if I had, say, like a black hole, I would not just have this metric. The metric would, I could change the coordinate system so that the radial guy going out in a radial direction is still null. So there's a specific choice of coordinates that Bondi liked. But then I now have a mass term that's going to be something in order of r. and I want to also have radiative terms. So I want to make sure that my metric will let me have black holes, but like this color that's really different, have some massive matter, have some radiation that's going to go out. And so basically what they first did was just find a nice gauge, so a nice set of coordinates for this class of solutions to Einstein's equation. And then they go about plug this into this funny PDE, and things simplify because of my larger R expansion. And I can actually kind of recursively solve this like complicated differential equation and see what the free data is. And so that's what they were originally doing. So this is basically like the much more complicated version of when you're writing down like linear Beckert solutions or some like I guess radiation, like you're gonna look at antennas or and great. Okay, so then the next idea is the one that was kind of the title of this section is notion of asymptotic symmetries. So I've trusted Bondi, Vedder, Metzer, and Sachs gave me a good choice of gauge for my metric. And now I want to play the game of what are the symmetries of it. And so if you take special relativity, or if you're playing with E&M, you would be used to, well, besides like rotation and variance in classical mechanics, like a lot of that is coming from, say, rotation symmetry. When you have a relativity, so you that you can treat time and space in equal footing. So you have this metric where it's like negative dt squared plus the dx in the spatial direction squared. And so there, what I would do is just say, I can do some, say, rotation or translation, and the metric is the same. And so there, the metric literally is the same, and that's an isometry. The interesting thing here is that as soon as I say I've put some like massive object at the center of my space-time, if I do a translation that would move it, it no longer looks the same. If I rotate it around, it makes it the same. But typically, like your more complicated solutions will no longer have as many isometries. So you want a notion that basically generalizes this. And these asymptotic symmetries are asking instead for you to stay in the same kind of fall offs that we were writing before. And you also only care about the ones that are going to act naturally at the boundary. And so that's what this quotient group is. So again, go back to the two kind of cartoon spacetimes. If I'm in Minkowski space, I have my four translations and then my Lorentz boost. So that's all it is. And if I have now Einstein equations, anything with like asymptotically flat spacetimes, I have no longer any isometries typically, but I have an infinite number of asymptotic symmetries. And that infinite number is going to be the fun thing. It's going to be confusing, interesting, and all that. Any questions yet? And so roughly, I want to think of it as I'm basically saying I'm taking a leader of my metric, and it's going to be subleading an R. So this is like a gross characterization because it's really different components are different orders, but that's roughly what's happening. And then what I'm going to do is if I solve for that, so I solve for basically my metric in the same fall offs, doing any coordinate transformation that keeps it roughly the same, I find a much richer set of solutions than my point array guys. And so in particular, what I'm going to get is I'm going to get angle-dependent translations. This F is a function of the night sky, so any function of the sphere. And then boosts and rotations are going to be holomorphic functions. And so the counting before would have been translations are just 1, 2, 3, 4, or 1, 2, 3, and then time. So 4. And your rotations would have just been your standard rotations and then all the boosts you could do. So it'd be 6. And now it's any holomorphic function, and it's any function on the sphere at all. So I could, if I wanted to, pick a delta function and just translate that guy. So many more things from the point of view of just this asymptotic symmetry analysis. And then the question is like, how do I see this physics? Because maybe when you're doing, you might look at like gauge symmetry, and you think of that as telling you that your physical observable should be gauge invariant. And so it's more of like what not to look for. And so it's weird that we're kind of coming back in and saying, no, look at these gauge symmetries. And I guess the special thing is that they have non-compact support. That. So to try to build intuition, and maybe this is more confusing if it's not, imagine that I didn't have any gravity, and then I want to just build, say, my time translation generator. I might take a Cauchy slice to take my filling vector, and then create from my matter stress sensor some charge that generates it. When I'm on a null surface, I can think of any two operators that are space-like separated should be commuting. And so in particular, I have like the interesting feature that all of those different locations are going to be space-like unless I'm on the same generator. And so from the point of view, say, of an operator at the same location as my anic, I am going to be translated, but maybe an operator over here wouldn't have seen it. And so you might think that an anic operator just along one generator could effectively just translate that direction of the night sky. And it turns out that when you have gravity, you have to modify it a little bit, and there is a soft term that's going to be important for my story. But otherwise, that intuition kind of works. It's like this null boundary is kind of separating up in different directions, and I have this ability to translate it in time separately each direction, and that's weird. So that should be very weird. So the weirdness is, again, that we're used to just time translation symmetry, and instead I'm saying for each direction of the night sky, I'm going to translate it a different amount of time. But the thing that makes it maybe less weird is, I think oftentimes when we use symmetries, we often ignore the fact that this isolation of things not interacting is kind of also implicit. So in high school, when I'm using momentum conservation, I'm not using like or energy momentum conservation for the entire universe. I'm using it for either my hockey game or my like a volleyball and a volleyball, whatever I got from the internet. I should have used it. I generated a better one. But basically, at least they are different masses. Like I'm often using kind of these symmetry laws in a very isolated system. And so the kind of fun thing is certainly somewhat intuitive. If I'm at very large distances, so I'm interested in scattering, the extent to which things are not interacting at large distances. Now, their kind of power law behavior of like Coulomb fields are still going to be important and actually are also related to these IR effects, and people here study that. But if I could just believe for a minute that when I'm far away, I don't really see interactions, there's a sense in which I might think that the kind of relative symmetries are like independently letting me translate or boost to different directions that are like far away from each other. So it's kind of rough intuition, but maybe you can poke at it a bit. So good. What are these going to be good for? How many people here when I was studying know there's theorem? Like, oh, right, yay, good, good, okay, awesome. So I okay, so Noether's theorem tells me I have continuous symmetries and then I get conservation laws out of it. Now Noether has a second theorem, and it's more complicated to derive or read, but effectively what it's giving you is some like two form that has some like nice like exact closure property. But I think of it as an analog of Gauss's law. And so what does Gauss's law tell me? It tells me I can take a pill box and like basically be at infinity or some surrounding sphere, measure the electric field there, and I know something about the charge distribution inside. Versus if I didn't have, if I had some other global symmetry, I would have to go around and like my like space time and I could measure like a Minkowski slice all the different distributions of charges. So I get some information about the charge distribution for free from the data of the electric field in that case. And you can do the same thing for the gravitational case. And so just as if I had a charge, a point charge sitting here, it's going to have a Coulomb field. If I accelerate it, I'm going to see that there's some region before it's like gone to some other kind of velocity where I have some radiation that's a different order in R. And that's going to propagate out to null infinity, like I was saying, massive things about to null infinity. And so in particular, if I just like take a time integral of my linear vector solution, I'm going to see that there's this kind of imprint of the scattering process on my like the low energy part of my waveform. And that's called a memory effect. So in the simplest case, it's literally just the fact that if I didn't have a memory effect, I'd be saying that my point charge that's just accelerated didn't radiate at all. And so that would be bad. That's not solving the equations of motion or constraining equations, whatever. I want to project down parts of the equation of motion for initial value formulation. So that would be bad, but instead it's not. So solutions to the actual like Einstein's equations or even just Maxwell's equations will have some memory effect. There's going to be some shift in the radiation field because of the fact that like the charge is scattered and they had some momentum or whatever. So the cute thing about it is that these things are all just kind of different basis expressions of the same thing. And so, for example, what I was just trying to motivate as this memory effect, because it's this physical thing, you don't have to worry about whether large gauge symmetries are something you feel comfortable with. You just have this memory effect. That memory effect, if I was in momentum space, would be realized in a scattering matrix as a soft theorem. And then the kind of cute observation is that it's the Ward identity that corresponds to the asymptotic symmetry I was saying was motivating the story. And so it's a universal enough pattern of relations that lets us find new symmetries or memories. And that new, like I guess the brand new ones that came out of this are what motivates the third part of the talk a little bit more. But for now, we can stick to being gravity. And so let's look at what the example would be. So I forgot that there's supposed to be there's spiraling, but I mean, you don't see it in real life, so it's okay. So something didn't quite PDF there. But I have some detector and I have some black holes or stars or whatever that are rotating around each other, maybe they fall into each other. There's going to be some gravitational radiation coming out of it. that my interferometer is gonna see. And say I'm like, I turn that into a statement about the metric, which is here, I'm gonna have something oscillating. It's not gonna look like this. It's gonna have like those little blips that you see when you see the chirps when LIGO measures a black hole invariant. But the point is that there's gonna be this shift in the field. And so that difference is its memory effect. And I can think of that as just having, say, two detectors are gonna be sitting wherever they are. They're on geodesics. It's a little bit of a different frame, but say they are. Then they have some wave going through and I'm gonna have them move a little bit. And then they go back to some set of duration that's a different distance apart. And so I can see that imprint of the wave passing and the memory effect, and the fact that I can kind of reset this baseline is just a gold demo, but we don't need to worry about that for this talk. And then, so that's what's happened. If I want to convert it to this word identity, I am basically seeing that in the same way that if I talk about like translation symmetry, I want to translate everything. So in particular, if I have my in and my out state for my scattering matrix, I don't just want to translate my in state, I also want to translate my out state. And so we're doing this for the super translations. And then the charges are very much like I was kind of trying to hint at before of this, my NF operator is going to translate that generator. But I also need to add in my gravitational term, some derivatives of the memory effect would be this charge. And I can just plug it in and I can evaluate this with a soft theorem if I wanted to with an NX symmetric element. Or otherwise, I could tell you like the solutions to like I guess these equations of motion are going to force the memory to be related to NX. So roughly, then the picture here is that whatever scattering process you had, you basically picked by picking your out states and in states what the energy is going to be, say, because I said I'm scattering those particles. Now you couldn't pick everything because Gauss's law needed to be satisfied, so there's going to be some amount of radiation. And that radiation is literally just like up to some Green's function, measuring the energy deposition for the in and the out states once I've matched things at spatial infinity. And so that's the statement of the word identity, and then the original derivation were more from a soft theorem point of view. But again, you can think of this as there is some part of the waveform that's just dictated by Gauss law that tells me that whenever there's an energy deposition, there's some memory effect. And then the derivatives that hit it make it so it's like a memory effect is discrete function form. So not that. And again, what is it for? So hopefully that was good enough in the sense that we have infinite symmetries. We have this function in the sphere, and then we have a holomorphic killing vector as opposed to just the 6 Lorentz guys. But the cool thing about it is exactly that second part tells us that these asymptotic symmetries include, say, super rotations. And so what that means is that I have my Lorentz group, and now instead of just my SO1,3, I have a Virasoro symmetry, Virasoro symmetry. And if we were a 2D CFT person, we have this big yellow book, you're going to see how much of that is 2D CFTs with Virasoro symmetry. I have a lot more of the kinematics helping you constrain those correlators. And so kind of the hope of the celestial holography program was that I could take inspiration from what happens in the 2D CFTs and say, well, what if my 4D asymptotically flat space times I have this Virasoro symmetry that's enhancing Lorentz? Can the kinematics constrain me so much that I get something good out of it? So that's the premise of the prototype. So any questions at this point? Okay. So finally, what is celestial holography and why are we doing it? So the statement of this program that again kind of came out at the same kind of order of operations in the sense of like the things in the previous part of the talk were what led to the efforts here. And a lot of people now are involved, but it's kind of from maybe Andy's group and like Moss Taylor and others in like the area and visiting. Basically, the point of this program would be, let's just conjecture or postulate that whatever description we want for our flat space hologram should be inspired by the asymptotic symmetries. And we're just seeing that there's this Virasoro symmetry, say, and these super translations can also be related to some currents. So we want to see if we can relate some sort of bulk flat space time in terms of the CFT living on the celestial sphere. And again, motivation for this, if you were from an APS CFT perspective, you would be like, that's weird. It's codimension 2. The celestial sphere is literally the night sky, not the night sky times time. And so it's a bit weird, but again, the motivation for it came from those asymptotic symmetries looking like there were some currents that live on the celestial sphere. by which I'm saying the Virasoro symmetry and the 2D CFT that is stressed and carry that solid market. So that was the motivation, and that's what we pushed in this program. So what I'm going to try to do is not bog down too much on like all of the technicals of the dictionary, but I can go into it. So let's emphasize again, celestial sphere is a cross section of null infinity. I probably can think of it abstractly, especially because I can super translate, but in practice, the easiest one to think of would be just like the U equals 0 or constant cut of scribe. And so I think of this little cone and just some circle or sphere, the cross section of it. And then basically that's where my theory will live. And the celestial guy is still going to talk about all the data on null infinity, but I'm often going to be smearing things along the generators of null infinity because then I don't have to worry about there being a null time direction. But in particular, so that's kind of a trick out of it. But the other thing that I want to keep in mind is the following. So, and maybe this is also useful for understanding the memory effects. When if I throw some ball in some direction, it's going to end up in that direction. So position and momentum space are correlated. When I go to null infinity, I can think of my massive scattering as whatever the impact parameter of that guy is, still going to go to the same direction, still going to hit the same generator of null infinity. And so I can really kind of blend my momentum space and space time pictures for, at least for masses, it's more straightforward, where any direction on the next guy I'm going to think of as equivalent to momentums, like the kind of 3 momentum of it up to the back is null. And then for this extra null direction, I've chosen sphere because I said I wanted to reduce it to the celestial sphere, but I could just as well have traded that out for, say, a point along here would be some null u coordinate. Or my momentum space guy is basically Fourier transforming in this direction. So when I look at the S matrix, I can think of it as being this holographic thing instead of this whole LSZ formulation, which maybe some people would have. If there's and so then after that, it's just a game of kinematics some level. So if I boost, then I see in my night sky that I like kind of the stars are moving around some North Pole. And so my Lorentz transformations of Minkowski space are going to be these global conformal transformations of the celestial sphere. And so that's not the cool part, right? The cool part was Virasoro symmetries. It was this super translations too. So you really have these VMS kind of group is much larger, and it's always there in these asymptotic flat space times. Super translations are there in kind of D for sure. But even just the level of just these global part, I can start to kind of take my scattering base and play around with it. And so that's what we were doing for a bit there. And in particular, so for example, we want to build this holographic dictionary. So there's just this positing that we want to recast our scattering as correlators on the celestial sphere. The point is, again, from the last slide, my Lorentz invariance is there. So my theory is Lorentz invariant. It also has point rate, like translation symmetry. But that 40 Lorentz invariance is enough for me to ask about how this thing transforms as like a global 2D conformal symmetry. And so the kind of cute thing is you can just see that if I put my massless guys and do whatever basis transform I need to basically diagonalize the boost that's in the same direction as that particle, then my massless like state scattering states, my A dagger acting vacuum, are already going to be boost eigenstates. And so like all I did was just do a Mellon transform in the energy. So I do some function, the kernel on the energies to scale it out and make it a boost eigenstate, and it's also primary. So like not only have I diagonalized the boost, I've made it also a CFT primary, some conditions on certain generators and everything that operator. So it's kind of cute. But basically what it means is I could always just go from my scattering matrix element, so things you study at CERN, and do an integral transform on it to get to some object that will look like a 2D CFT correlator. Then all the rest of the yellow book you kind of have to start to question or play with, which is a little bit of a downside of it, but you could try, right? And so in particular in this dictionary, the first things that are fun are, okay, the global symmetries, the Lorentz invariance, conformal symmetry, yay. The memory modes and my celestial currents, cool. Those are the things that I'm doing nice. And then you can play around with like various like IR things, whatnot. And the next thing I just want to focus on instead is this collinear limit. So what do I have? If I had a 2D CFT, and so this was the attitude that was taken, even though it doesn't necessarily bear out exactly as simple as that, you could say, well, I have Lorentz symmetry. That means I have 2D conformal symmetry. But I don't want to think of my 2D theory as the Euclidean theory that's supposed to with rotate the Lorentzian 2D theory, blah, blah, blah. I need to kind of redo some of that part of it. But if I could pretend that as much of it as like a normal 2D CFT as possible, then what's the game I would play? So CFTs have this nice feature where the operator product expansion will converge. And so then I just need the spectrum and the OB data to tell me like how to compute correlators in a CFT. And so the spectrum comes from this change of basis that I was telling you, where I'm smearing along the infinity. But then if I wanted to say, well, what would be the OP data, these operators coming together? If it's what I just said about the fact that the position, momentum, space are kind of the same as the direction of the then you would think that the collinear limits of scattering will tell you about the OPE data. And so that's what people were doing. So at some level, if celestial CFT just worked out as if nothing still happened, you'd be trying to bootstrap amplitudes from their soft and collinear limits, with the soft limits being those currents we're talking about, like super translations and other memory modes, and the collinear limits being literally a coincidence in the night sky. And you can see like in some approximations, you know what the splitting functions are from amplitudes, and you can do those model transfers and get them out. So that would be the goal. And then people try to play with this. And so in particular, so maybe I don't want to put too many equations because it gets a little bit too much. But if I have an amplitude and I have a collinear limit, there's a certain splitting function that I just know what that amplitude looks like. And then I do the basis change I said before, and I get some vector up front. And then I can try to ask, like, what does this thing look like? What symmetries do I have? If I treat it like a 2D CFT or not? And the thing that I want to just say, rather than show, is I'm going to turn the crank blindly as if it's a 2D CFT, looking at these collinear splitting functions of amplitudes transformed to a basis where there's some currents that could be at like integer values of the correlation. Okay, like some trick there. But I'm going to pretend it's a 2D CFT. And then Andy inference on this interesting additional symmetries coming out from these collinear limits. So everything in the first part of the talk is about soft limits, giving me some symmetries. And then suddenly now it's like I'm taking collinear limits and getting symmetries because I'm treating it like a radially quantized 2D CFTs. So from taking a step back, it's like I want holography to work in flat space really badly. I'm going to take what's the first thing I can do if I didn't want to do string theory and I wanted to like do the basic thing for say ACFT without if we never had string theory, we probably have like some Brown and maybe. And so we look at asymptotic symmetries on both sides. We'd have a CFT 2 with like some 3D gravity. But now flat space gave me the same CFT 2 for 40, so we like 40. Okay. So we have those symmetries, great. The symmetries told us that it looked like a 2D CFT. We know 2D CFTs when they have Virasoro number symmetry have a lot of power. So we're going to pretend that we have that. We're going to go push it, turn everything to boost basis. We're going to say collinear limits should be OPEs. And from that, we're going to try to extract all the types of things we would get if we had, say, holomorphic functions in our collinear limits in our CFT. And so really just brute forcing out like this collinear limits would give me some structure because of the 2D CFT. They identified like a larger symmetry algebra that's not quite of the same structure. So soft guys are just always there. Momentum conservation and angular momentum conservation will give you these things. The W-infinity symmetry is like an exact symmetry of self-dual gravity. And it's a symmetry you're seeing at 3 level, for example, in the one case. But it's a little bit more subtle in it, and it causes really good things and then also some confusion. So there's 2 different types of symmetries. And the cool thing is that basically once we understood that these symmetries are related to self-dual theories, then various other people with different hats knew what to do with them. So for example, like we had Penrose diagrams, but Penrose does a lot of things. And another thing that he did, well, it's within the class of like Twister space and whatnot, so it's not related, is understand kind of like nonlinear graviton constructions and really like how to geometrize like the space of geodesics or like what different solutions are that are self-dual. And so these self-dual theories have some sort of way to build more self-dual theories by like changing some bundle structure in my Twister space. And so some people from Oxford knew how to deal with that. And then people like Kevin Costello, who worked with Dominic Otto, but more Kevin and Natalie Paquette, and then Atul Sharma, were able to like find a very specific version of twisted holography, where basically they're doing holography and there's a Twister space in it. So that explains why they're related here. And they find the same parallel algebra from floating elements. And so what was neat about that was, I can think of it on the next slide, is suddenly you have like an actual hologram just from all these little ingredients you're kind of begging for from the bottom up. And so what's fun, and this was the start of our like science collaboration that a couple of years ago we've now had it, is that if I wanted holography and I wasn't just trying to say, we're all doing quantum gravity, trust me, this works. There are kind of 2 different approaches one can take. In practice, everything I've done is very much bottom up, or at least the way that Andy uses the word bottom up. So I'm mentioning symmetries on both sides. I have my asymptotic symmetries, and I'm trying to say that they're there in the CFT boundary theories too. I have consistency conditions. I can try to put a unitarity in both S matrix, That's not going to look like a normal 2D unitary CFT, but should do something. I try to add in some reasonable expectations, like I have a graviton, so that means I have all these memory effects and whatnot. And then I go from there. If I had a top-down construction, that would be the kind of motivation in the first or second slide, where I had said that string theory gave me a hologram, gave me ADS-CFT. So we would like, if we like, so a lot of people are like, okay, I still believe in string theory. And so they really want to have that top-down construction to believe that you don't just have symmetries matching and then like you actually know what the next ingredients are that you're missing or what approximations you're making. So that's the gold standard. And then curiously enough, at least in this case, we had it. So if I was doing ADS-CFT, top-down is great. I have like type 2B strings on ADS5 versus 5, and it goes 4 square nulls on the boundary. And the bottom-up step would be stuff that I find more interesting, or for entanglement is geometry. How do I reconstruct the both? Or like matching symmetries on both sides, maybe the simpler part of it, but it's richer in flat space. So this is all good. Taking a flat limit is hard because I often don't end up in my like flat 5C, say for example. I end up with flat 10B. But now, because of this kind of really brute force, I'm going to make this 2D CFT work. I'm going to look at the collinear limits and get some sort of algebra out of it. Suddenly we have a top-down construction that has exactly all the ingredients we're going to ask me for, and is in some sense an asymptotically flat hologram. It's on burn space, has some like defect in the origin or something. So basically what's kind of fun is that this kind of blindly trusting this additional collinear symmetries or something universal that I wanted to have led to, like, say, these theories that are kind of like stronger generalizations of like self-dual gravity or whatnot, where you really have a 3D construction and they have the same parallel. So that's cool. So we really have a top-down and bottom approach implementing each other. And I think that that was like a big milestone in that program. And so then I just want to ramble for like the end of my talk about things that I'm excited about. So what I liked about there's one takeaway that would come from this program is remember that there are more symmetries than like Poincare group for asymptotic flat spacetimes, and how the hell do they like constrain quantum gravity? Yeah. So what I like though generally is there's a lot of cool things a lot of cool people do that I wish that I knew more about, and like, you know, we're kind of making the things as we go with this celestial program. So like, okay, let's see what else we can latch onto. And so the amplitudes program obviously cares about the S matrix. You know that there are amplitude results that are super simple, but the ways to get to them, all the Feynman diagrams, even though they're straightforward, they're tedious. There are many of them, you can't even always like compute them efficiently or whatnot. So like they would be looking for some other rules to find a description of this S matrix, not through the diagrams. So in some sense, it's a similar spirit. And it from qubit, obviously like kind of the more interesting physics somehow is like black holes and not so much just rooted to the boundary of ADS. And so you're also interested in like the flat or like not like necessarily ADS in principle. And then the bootstrap program, very general statements that can be made about unitarity and CFTs and whatnot. So a lot of fields not only would care about holography from different angles or think that they understand really like how to extract some S matrix elements from like flat limits of ADS. And so it's all about the subtleties of like actually having this intrinsically flat hologram. And so two things that I think are important or fun to play with is really, I like bottom up, so I'm going to stick here, but looking at more like how do I have like both reconstruction or an RT formula. So this notion of a boundary theory whose entanglement structure is related to just a bulk geometric quantity. When I just do naive flat limits, for example, like somehow like the holographic screen becomes much more important in the flat space version. Because you just can't make geodesics end at any 2 points you want in L infinity, for example. And that leads to some interesting confusion of literature that's fun to work through like. And then the second thing that I think is a super fun direction is that in the bootstrap community, you have everybody who's studying conformal colliders. And so back in the day, people were using like ANIC correlators to really do like precision tests of PCD and bound some like anomaly coefficients. So like we have this positivity ANIC and there's fun games you can play. But at the same time, most of what I'm saying with celestial CFT, those have just played the role of, oh, look, I know there's a memory effect. I know there's a super translation symmetry. So nominally, there's the same operators. They're both using celestial conformal blocks in some sense. So you're decomposing these correlators in terms of kind of erupts of the Lorentz group. And maybe one could say that by accident here, these guys are interested in like IR finite observables. The ANIC is protected in some sense. And then when you're low energy, I don't have translations. Like translations are trivial, so I just have Lorentz group. So in hindsight, maybe that's the accident of why they're like the same physics. But these guys are my hard charges. And so anything interesting that the person can say here, we can try to say here. And I guess the problem is that here we're always kind of starting with a single particle external operator instead of both inclusive quantities and like NX or other hierarchies. So that's a fun bridge in just to straightforwardly triangle because you know the kinematics is the same. And so I think there's a lot of fun things to do with relating to understanding both like the scattering story, like conformal symmetries, and understanding that like why thought limits of ADCFT are so much more subtle. And if that is really the right approach to talking about holography. And in particular, I think those kind of like saying starting from the supersymmetries symmetries and are a good way to go about doing that. And so that's all I really wanted to say. So thank you guys for your time.
Okay, perfect. Yeah, we've got lots of time for questions. Babe, yeah.
I'll ask a general question. I mean, I usually think about if you have a black hole,
Yeah.
then you get a Hawking radiation to the boundary, and the boundary will be naively, I mean, the correspondence context will be finite temperature CFT, but it's like a 2+1D, for instance, physically. I mean, it depends on where the ball is, but physically, I would think about, it's a finite temperature CFT. I mean, if you have Hawking radiation from that.
So I think the question is just more like, how do I
How
get
do you
around
relate
it?
it to the CCFT?
So for the celestial story, like I mean, strictly rules of the game as far as once I have my asymptotic boundary, I go to the celestial with my reducing it, for example. Like I can choose to do it even if it wasn't, even if the better representation was the Brownian thing or something with the temperature and some time like boundary regulating it. The question though, I think, is that somehow like I don't know how to do the analog of say this island story or however you want to like avoid like ending up in a thermal state when the black hole evaporates in this picture. And I also wish I understood better the extent to which like the kind of the bath they add on is, but like there doesn't seem like there's any like notions of like asymptotic symmetries or like much of the flat space besides the fact that there's like some leaky boundary conditions, I think. But so I would say that it's a challenging question to understand like how even our knowledge of say living with black hole evaporation and holography can be imported to the flat space theory. But it's not a very obvious that I couldn't just as well like capture anything that you wanted to have like in like some behavior at long or infinity or oh my god, great.
Maybe I'll ask one.
Yeah.
So, okay, you're saying just with a pure flat space theory,
Yes.
you have all these different scattering experiments you can imagine,
Yes.
and then there's some connection between the answer to those and then this possible 2D CFT calculation.
Yes.
Is it actually, I remember people saying a while ago, like for flat space gravity, that maybe scattering amplitudes are the complete set of questions that you could ask. Is that
So
your perspective? Do you even believe that? Or?
I mean, so I think I believe why, like, I believe in the reason why they want to believe in the sense of like, so typically say that the metric is like not supposed to be like a perspective on quantum gravity, right? So that everything needs to be tethered so much in the boundary, and that's the extent to which I think they use the statement of like all the good observables are asymptotic observables, and the S matrix is that. So yeah, but I know there's a lot of fun things in practice where you're always kind of pretending to fix back on that. So I think I believe it for the technical reason, but at the same time. Yeah, we do things like I don't mind playing with the like say data Swin diagrams and things about being there, but
Good.
but I think yes, I'd say yes.
Yes, please.
Thanks, sir. I have a question. So connects matter with
Yes.
phase transitions and critical points.
Yes.
Sometimes have emergent scaling variance and conformal symmetry. And this sort of symmetry emerge like phase transitions and critical points.
I would have a hard time thinking of it as emerging from a phase transition, but the one thing that is maybe okay, you're gonna probably this is probably not the correct like thing to transition it to, but you could try to look, for example, at say what boundary conditions would I need in ADS, and then just take a flat limit and then get like asymptotic flat spacetimes. And so definitely not a phase transition thing, but there is an emergent symmetry that comes in that flat limit because I can see that if I didn't set lambda to 0, I would roughly have to turn on like the overleading part of the metric. So normally I do like from gram gauge, leading metric is just like whatever round metric on sphere or cylinder. And then all the stress sensor is like in a subleading mode. And basically like in the flat limit, like the equation gets kind of restores back. So I think what I'm saying is that there's a sense in which sometimes symmetries get restored when I tune factors, but I wouldn't call it, it's not the same in the phase transition sense, but there is something emergent by like limits of things. So like if I just had ADS with like leaky boundary conditions, I don't have that asymptotic symmetry even in the ADS one. When I go to the flat limits, I might have a much larger one. But that's not, again, in the same way that you're asking those questions. Yeah, basically solutions in the flat might be different from the limit of the solutions of the only thing that I want to point out. But,
Yeah, Francis?
In Virasoro CFT,
Yeah.
there's an analog of length. We can extend the Virasoro algebra to extend it with some global curvature.
so okay, so to the extent of like, are you thinking like of like work CFT or what sense do you mean? Because like I'm saying like I have Virasoro symmetry and then I can have other like Katsumudi symmetries or other things,
Yeah,
like,
yeah,
other
Katsumudi
independent
symmetry.
are not talking to each other.
Oh, okay. Then.
Versus some people would try to like take the W infinity symmetry as having like a Virasoro inside of it. So I would say that basically whatever the gauge theory content is of your theory, those asymptotic symmetries would be like the things you'd have on the right hand side. So if I have like some like photons in the bulk, I would have a Katsumudi symmetry from that,
Yep.
plus I would have Virasoro symmetry with Virasoro from gravity, and then I could like make a list or whatnot like that.
Alejandro?
How much of this depends on the fact that we're 4 dimensions and therefore the
Yeah.
sphere is 2 dimensions?
Good, so I would say the Virasoro story is very much this 2D special thing. The super translations are always gonna be there in the sense of like, so one thing that's different in higher D is kind of like the memory effects are like a different order in relation to like, say, the Coulombic analog of like the charges accelerating. And so there's a sense in which it's less obvious that maybe you had to have things. So for example, if I like look at this reading memory effect, the super translation that's happening is at the same order in R as where the memory effect is actually shifting things. Versus there's some extra green structures that kind of probe deeper into the bulk, but there's still universal soft theorems. So there's a version of the story where you can make all of the super translation stuff go all the way to higher D, but there has been some debate in the literature about that, which is fair because basically like kind of R divergences are also super like important in 4D and there's like tied in a certain way to that. So basically subtle R divergences are a 4D problem. Super generalizations could be debatable, but they are strictly there in the sense of like this null surface has that symmetry in higher D super rotation stuff.
Yes, please.
You mentioned particle physics observables.
Yeah.
Can you give a few examples?
Sorry, it's in the sense of
Examples of what would be.
sure. So for example, like one of the things at the end is this. So memory effects, I wouldn't be saying that would be more of a gravitational wave thing than the particle physics thing. But the particle physicist would measure, say, energy in my color emitter. And so, for example, like those NX operators that people are looking at, those are my hard charges for my symmetry. And so as soon as I add gravity, there's a universal relation between those variables and my like waveform ones. So that's like those types of say NX or like trying to build other kind of composite light ray operators that have like that are not iron inversion, I think is like one game to be playing with in the space of like what are good asymptotic observables. And that's the question that I think you'd ask in a particle physics context about like, I guess things being gauge invariant or like large gauge invariant, rather than just like in the gravitational context of
That would not be only limited to
Yeah.
calculations that even work out. I mean, as you mentioned, calorimeters now, this you actually mean experiment.
I do know I not myself. So what I'm saying is I'm co-opting like a lot of other people's works when I start to say that. So what I'm saying is there is definitely statements of like, if I have like my NX operator effectively can be approximated as like a time interval of the energy in a given direction, right? And so these 2-point functions of like energy correlators have been like tested and like the behavior in the collinear limits like appears in these early like UCD papers. But I only kind of come across them through like more citing them in Hoffman-Malvicena and then like people like Ian Moult or whatever who actually are starting to, computing things to much higher loop order than I would, but I can say that last part of it, the word interface, then tell me what the memory is, but that's easy, but yeah.
Jeremy?
I was curious about the top-down construction. So does it actually realize like some kind of duality between this whatever's from gravity to 2D CFD in the same way as ADS-CFD does? Or is it like a weaker version of that? Like
I think it's a more esoteric version of it. Like so it's not weaker in the sense that it's exact, but the issue is that it's like you're taking, I think if I understand the bigger picture version of it correctly, it's like you want to take like kind of like n equals 4 normal thing, and then you're like quotienting by some like I don't know if it's a supersymmetry or whatnot, but there's a way that they're kind of like, going down to like some sort of like cohomology sector of it. So if it's exactly true in there, you know, like all their corrections to whatever, like limits you're taking, it's like there's stringy things happening, but it's a funny, like topological version or something like closer to that. I'm gonna use the words a little bit off, but it's exact, but it's weird because it's not like Einstein gravity, for example. That makes sense.
Oh, looks.
I'm still trying to understand the motivation.
Yes.
I'm struggling.
Okay.
I can
Okay.
imagine.
What do you
Smart.
do? Okay.
I can imagine you doing this because there's a long program where at the end
Yeah.
you're comparing to some real thing in the real universe.
Yes.
So you imagine that you explain something about inflation, black hole physics.
See, that's okay. I actually have backup slides for this purpose, but this is not the right way.
And is that the idea eventually, and you're just in the early stages, or is that?
I can be a cynic and say what different people's motivations are. So like I'm a child of string theorists, but not a string theorist myself, right? So I think that we're like in this postmodern whatever version of like we don't necessarily believe in string, people believe that it's really cool. And so we love the math problems that we do, and like so like at the very short scale, I know what I'm doing. I love the physics questions that are this little math problems. I still think the motivation is more connecting frameworks. And so like if I try to be a cynic and think about what I'm most excited about, you know, when I say I do quantum mechanics and relativity, what do I really mean? I mean that somehow I believe as a theorist that there's some compressed version of this large ass canon, and that's the goal that I have. So Juan and his like talk at strings would have said, okay, why do we do quantum gravity? It's literally because, okay, we know these things, we want to merge them, we want to condense them. And so that's literally what I think a lot of us do in practice. Like we're motivated by the fact that we think that this literature can be compressed with simpler things. And then is the best way of doing it to like add one little thing? Maybe not. We have like all these dualities in our like I'm saying web dualities. I think it's a fun thing that somehow the fact that we have dualities is a statement about different branches of mathematics and all being connected in the physics guiding that. But it's that redundancy that is this interesting structure. And in our case, we basically had like this IR triangle story came because some people knew both amplitudes and knew relativity. And this is gonna go crazy for everyone. You know, the first like IR triangle, even though it wasn't called that yet, was just Sasha seeing that the same equations appeared in two different papers. You could automate that, right? Like this is like reverse equation search would get you that. And so as much as this is what I felt like in grad school, you know, a lot of crap that you're going through, I still think that like there's like data science you can do for this field. What do people work on? We get a little bit isolated. And like, can we try to really solve these problems? So I think I'm most excited about is the fact that like I care about that canon, and I think I've appreciated that in hindsight. So whatever, I can ask that a little. So this is what I care about as like a side like answer to because I know like that it's like it's a big question, right? Like why do we actually do what we're doing? I think the reason why I do what I'm doing is because we are like trying to just connect different frameworks. So and I think longer term, that's the place I mean. And basically, I think that is the thing that motivates us. So like we want to understand like how kind of frameworks generalize in different ways, and we're always just trying to link in different things. So that's what I think of as the motivation. But I do think that it's part of this thing of literally trying to see a framework that understands like a simple explanation for like a theory that encompasses both quantum mechanics and gravity, right? That is still like the correct like overarching picture. But yeah, sorry, how about, so how does that make you feel as far as it's just like
It sounds like you're not trying.
the second?
It sounds like you're not trying to do something that connects to a measurement.
No, I think I am. So what I'm saying, no, let me push back.
I just thought you might say that eventually we have this 2D theory, which we fully understand.
No.
And a bunch of calculations are really easy then to tell us stuff that we couldn't do.
I don't think that would be as honest. So what I would say, the first thing I could say is, okay, we can go and we can wait for like 5 years or 10 years at Lisa, for example, and they'll go and they'll measure that some like extra U integral of my strain is related to some quadratic integral that is the angular momentum. So like there's a memory effect that comes out of it that, you know, this predicts, right? So you have little things like that come out that are the physically testable thing, I would say, right? And those are more on the side. So like there is something you can test. But I think the thing is like to what extent your frameworks are consistent or not, like we're driven by mathematics. And then at some point you do want to connect to experiment, but I don't think that's the goal of what I personally do. So like, I see myself as like, I have this beautiful mathematical corpus that's like playing with questions that are so far away from experiment that I don't really get to latch onto it, but I can try to clean this corpus up as much as possible instead of adding more shit to it. We're looking for those compressions. Those compressions are the breakthroughs. And then later, if we really had a good map of that kind of set of true statements building off of each other, then we'd be able to tie it to experiments. And I care about that part as the thing I care about. And I'm happy that other people are right now, like, what's experiment I can do right now? But like, I like, that web of knowledge, or that kind of knowledge graph. So sorry.
So
So that's, yeah, that sounds like a good place to stop. I would invite you to hang around, finish the food and ask any questions you might have either about, gravity or like life as a theoretical physicist, or perspectives on theoretical physics. So let's thank Sabrina one more time.